Hello, and welcome to this episode of Starting Line from Off the Track. My name is Peter. This episode, we welcome back our friends, the 2020 German F1 in Schools National Champions and 2022 World Finalists, Sonic Boom. This episode is a continuation of the Starting Line series. This time we're focusing on CAD and Technical Drawings. You'll be learning about how to choose CAD software, the different software formats that are used, and how to model in CAD. We hope you enjoy.
Hello and welcome to this special episode of Off the Track. I'm Enes Isayan, the host of today's episode. I'm joined by Yannis Gorzir.
Hello.
Florian Wolf.
Hi guys.
Benjamin Galvin.
Hello.
And our special guest for this episode, Bilal Yildirim. He's an engineer at Alfa Romeo F1 and even more important, an F1 in Schools judge, but more on that later. Today we want to discuss some of the most crucial parts in designing your car, which are CAD and technical drawings. Your CAD data is the basis for all manufacturing processes. It therefore determines the quality of your final car and can make the difference between losing and winning a competition. But starting from the beginning, Bilal, do you want to introduce yourself?
Hello everybody, my name is Bilal Yildirim. I'm digital performance engineer at Alfa Romeo Sauber F1 team and I'm working there since 5 years. I started as an engineer in the aero department and from there on I switched into a more cross position between IT, engineering, manufacturing and other departments, which is taking then the lead on to remove all the digital bottlenecks we have, which should improve then the development of our race car.
All right, great. So moving on, there are many software options out there, and sometimes it might be overwhelming trying to choose the right option for your team. Florian, do you want to give us a quick overview over the options that a new team has?
Yeah, so we are a German team and here in Germany we use Solid Edge, but more on that later. First of all, I think the most common one is the Autodesk version Fusion 360, or at least they use also Inventor, because it's, they have a really good student program and it's free for all students. The same is here in Germany with Solid Edge, which is used by most teams because it back then it was mandatory because the local F1 in schools had sponsoring with Siemens, so Solid Edge was mandatory to use for all teams. And right now we are still using Solid Edge because it has many opportunities and is really similar to the industrial SolidWorks or Siemens NX, which also some teams are using, by having sponsoring or something like that. But I think down at you guys in Australia, you use mostly Autodesk. Is that right?
So Autodesk is still probably the most prominent program we have here in Australia, mainly because it's a sponsor of the competition, as well as like you said, it's a fantastic student program. It's free for most students, and it's also a rendering tool, quite a capable rendering tool. Inventor is also quite popular, and another one that's used by a lot of, especially older based schools that have been competing for at least a decade. They also tend to use CATIA.
All right.
But it's a bit more complex and complicated, and 360 is most commonly used.
Yes, because I think it has also a simple structure. CATIA, as far as I know, is also used in aviation industry, and also the freeform surface modeling there has a lot of opportunities. That's a problem we have with Solid Edge. It's quite complex to get the right surfaces you want really to produce. So I think there's also a feature in Autodesk Fusion. Therefore, it's quite good to use for F1 schools because you have those complex shapes.
Bilal, what did you start? I mean, you competed in the competition as well.
So I actually started with CATIA, and that was like 15 years ago. And then I found out it was mandatory to have solid edge, so I had to switch to solid edge back then. And but the truth is that if you want to do really more complex surfaces, generative shape design, or more parametric designs, it's I think you rather go for CATIA or NX, or then but solid edge I think or Fusion 360 are good for beginners. And to get the basics, as you would be quite overwhelmed by the amount of function and complexity within the, I would say, NX or CATIA. Oh, actually, it's now called 3D Experience. So yeah.
I mean, I guess for a new team starting, it doesn't really matter which software they use, like from which company, as like if they start with a beginner software like Autodesk Fusion or Solid Edge, it doesn't really matter which software you choose. I mean, don't put too much time in trying to choose the right software. Just start right away.
Yeah, I think it's necessary to know the software and not to change every year, because you can design your car in all softwares, and to learn another software, it's very expensive in time, and I think it's not smart.
I totally agree, yes, and that's the same thing in our team, because we started on using Solid Edge. We also would have the opportunity to use Siemens NX, but we're quite familiar now with Solid Edge, so we just stick with Solid Edge for the World Finals.
So you talked about learning a new CAD. So talking about that point, I mean, learning CAD is like learning a new language. It's important to learn the vocabulary, but even more important to practice. So how did you guys, we only have like engineers in this podcast, how did you guys start achieving the skills for constructing such a complex model as an F1 and Schools car, but also like other complex parts?
Yes, F1 and Schools is a mid program in our school, but the teams participating in the competition, they did it just for a year, so they had really just the basic knowledge of Solid Edge. But it was great to have someone who knows these basics and could teach you some know-how, but participating the second, the third, the fourth year, it was our turn to gain some knowledge by watching tutorials, trying out new things. It's just a thing of experience. You have to keep on designing cars, designing something, just for fun, but you also learn by doing.
We had quite a unique program at our school where F1 Schools was mandatory for iSTEM students, which is practically it's a course that we take on, basically focuses around STEM, so science, technology, engineering, mathematics. And within iSTEM, we have a mini F1 Schools competition against each other. All the students have to design their own car, and that's actually begun in CATIA. So in about year 8, I was taught how to use CATIA from the teachers. We basically were given an initial template. From there, we could explore the tools further and slowly develop our skills. And some of the students would then go into the F1 Schools competition. That's how we selected teams. But within our, I think, second year of competing in a professional class, we switched to Fusion 360. This was just so we could have a more capable rendering tool. And from there, we sort of self-taught ourselves, but also learnt from previous mentors. Our team had quite a few contacts, and our school had quite a rich history in the local competition. So from there, we were able to teach ourselves the new program. And as you said, it's just learning from doing. The more time on the program is more you learn.
And CATIA, with which workbenches did you start?
It is a fantastic question, and I cannot remember.
Okay. All fine.
Yeah, it has been quite some time since I've used CATIA within the competition.
Okay.
All right. So starting your CAD construction may seem hard in the beginning, but there are many different approaches which will get you to your final model. But starting with F1 and Schools cars, what approach did you use, Yannis, in your old team when you started?
I think the first time we started to cut pieces of the car, of the block, and then we had a very edgy car after this. But I recommend 2D sketches and then design the car in 3D. So we started one half of the car and then we mirror it. Yes.
Yeah, that's basically what I think. There are two basic approaches, as Jan had said. So the first one would be to subtract volume from the ruled F1 model block. But that's very complex, and personally I think you could not get those shapes that you actually want to have in the end. But that's why we use the other way around. So we start building up volume by using 2D sketches and then building the 3D model from scratch, basically.
We did the same thing where we build up from initial 2D sketches as well, loft the main body and then work around just molding the shapes.
Well, it's still interesting to see most of the teams who are going to participate the first time, they're just using the basic operations like extrusion or cut out. And it was the second year, I think, we found out that there are functions like a loft or sweep, which helps you to get the exact shape, because as an engineer with your engineering team, you have that shape in mind you want to produce, and that's the challenge. And just having those 3D operations, extrusion and cutout won't work out. So you really have to work on the understanding of the program, the different operations, the opportunities to get those shapes really.
Therefore, I would recommend to learn the commands of the software, and it's important to know your software, and then you could produce your forms that you think of.
What approaches are there in real F1? Like if you want to design a car?
I think it's usually you start with the boundary conditions. It's so basically where are your design limits. That would be as well, for example, for F1 in schools, you potentially start to set up where your area is or your volume, where you're allowed to design. Then you start to think about possibly about the transition between these areas. You think about what's the task of each volume, for example, with the front wing, rear wing. You think about what its purpose is. Based on this, you start to design the wireframe. Then with the wireframe together, you set up then the parametric possibilities. Finally, the last step is to create then the surfaces or your solid bodies, and then you go basically into checking that stuff.
Yeah, and that's interesting. That would be another question. As far as I know, there are also different approaches in designing those surfaces. So you have these basic operations, extrusion, and that's already a volume, but there's also the other approach by just using surfaces. You connect to your 2D or 3D sketches. So I think in Formula 1, the real F1, you just use the second approach. Is that right?
Yeah, the first one would be more of a simpler shape. For example, let's say that something like this here, you would for sure take something like a solid maybe, and then you would start to get the edges right, and then be able to control the shape by that. But if you really want to think more in a maybe organic shape, or more into a shape that is multi-purposeful, then you might be better on with going for wireframe and surfaces, and then going from there onwards.
No, right. Yeah, that's interesting, but I think it's very complex. As we tried that out for our World Finals car, because we also see the progress or the opportunity in using surface modeling, but it's way more complex.
Yeah, the complexity comes from the possible controls you can have, and you need to the complexities as well by thinking about which parameters you want to control after you are finished, and then you need to basically design more, thinking a couple of steps in advance.
I do really agree. Yes.
that makes actually the complexity, because you might not know what for feature might fail when you're finished, and then you try to update the complete model, and that's why I think it's quite crucial as a beginner to understand the basic functions, where the limit of the functions are. For example, with the extrude, it goes only in one direction, and it can only for example, a 2D sketch, you cannot extrude. Then when does 2D, you cannot extrude it like this, only in that direction. Then you can have the same then with sweeps or anything that moves then along in 3D. But that's like this core complexity, to be able to think a couple of steps in advance to solve then in your current process that shape.
Yeah.
I think, Florian, for some of our regional cars, you constructed the chamber rotating the part. Could you elaborate on that maybe?
That's the rotational extrusion. So you have that basic 2D sketch and have an axis. You want to rotate the volume around. So yeah, you only create more or less the half of the volume and then rotate it around the axis.
But but then again, still based on a 2D shape, and then you basically rotate it around the axis. So it's something, to really get, for example, a nice shape around the sides of the car, or around the front and the rear, or around then the mid of the car on a F1 and a school's car, and for example around the pressure chamber, and then everything around this. You usually start then to use maybe splines, and then these kind of components together with points to be able to control then that.
That's a complex surface modeling, yes. But the question is if it's really necessary for the F1 and schools competition. I think when it comes to the professional class, maybe, but just for the basic start for F1 school, for new F1 school teams, I think it's more or less the best way to use those basic ruled geometry operations, extrusion, CAD, and maybe loft. But as we said before, it's the most important thing to get familiar with the software.
Yeah. So I think best approach would be first year you start with classic extrusion, as you said, and with these, I would say, more the starter functions in Solid. Once you understood them, you can then try to take your time for a couple of months to understand these functions in 3D, like points, lines, splines, and whatever you have available. And then you try to get these things together, and then trying to create surfaces with that. And there you can, I think you won't find that much in the internet, right?
Yeah, that's another problem, yes.
As I was as well looking myself before I started here, you're not able to find that much about this in the internet, actually.
Right.
And these are more than shaping as well. What you find, which is is okay, but is not gonna be that stable when you wanna change the shape of it.
Yeah, I think Yannis and his team Beyond, they used another method to produce their 3D shapes by using the curve table, I think it's called.
Yes, you have parameter that we write in this table and values, and then Solid Edge creates a sketch, a 3D sketch of that, and then you can use it to do freeform surfaces, and after that you create a part. But I think it's not recommended to younger teams, because you have a very you must understand what you think in your head, and you must type it in values, and that's very
But that
difficult.
goes a bit into generative design, or not, to basically set up the parameters and then creating a surface. And then did you do that over certain macros, or how did you approach that actually?
In Solid Edge, you only can do it with an Excel sheet.
Which is fine,
and
for a start.
Yes, and there you can type in parameter and values, and then it only creates a 3D sketch, and then you have to create freeform surfaces and then the part of that.
Yeah, so I think it's in some way it's quite limited because you have to fill in these coordinates into an Excel sheet. The first thing is it's quite abstract to think about those shapes. The other thing is that it's not parametric modeling, which then brings us to the next question, I think.
Yeah, like how do you construct a car that you or a model that you want to change afterwards? What options are out there? And I think it might be quite helpful to like have a parametric CAD data that you can change in order to do like different design approaches and maybe test them in a virtual wind tunnel. So yeah.
First of all, I think it's important to explain what is parametric modeling. I think Anas, you might give an excursus.
Yeah, so basically, I mean, you worked with it, Florian, but basically is setting up your modules so that you can change certain parameters without having conflicts in your construction, in your CAD data. And that helps you like varying the different designs. So if, let's say you're trying to do like 4 or 3 prototypes from a car and you want to test them in the virtual wind tunnel, you don't want to construct the whole car again. So you just construct the car parametrically so that you can change, like, I don't know, the wingspan or something without the whole CAD model crashing. And then you could do analysis in CFD wind tunnel. Yeah, and maybe how did we do that at the national finals? And then also I'd be interested how the others did that. Like, how is it done in the real F1 world? And also, Benjamin, how did you work with that?
Right, so we basically start in Solid Edge. You have those different files. So we start in a .par file. So that's the basic part. And as we said before, it's the combination of 2D sketches first of all. So we define all those parameters there, and we can write them in an Excel down so we can change them later on. And then we create those surfaces or volumes out of that. And all those parameters are variables you can write down in Excel and change them later on. The challenge is to have a model that will not explode later on when you change any values, because that's mainly the problem, yes. And from that .par file, you can do splits in parts, so the interrelations are we can keep those interrelations up without changing every single part from scratch.
Maybe for those who didn't use Solid Edge, just because Florian said .par, that's like the native format in Solid Edge.
Right.
Ben, how did you work, or how did you try to do like a car which is parametric as possible?
So I know within Ascension, we did a lot of rapid prototyping. I think in total, there were about 200 different prototypes in which we properly tested. And one of our engineers, Fefe Webster, who was the one who actually molded the car, from memory, I believe what he did was he would go through and change each individual component based on small millimeter fractions and then save as a new file. And we had each individual component of our car split up. So if we wanted to test a completely different rear wing, it wasn't too difficult to take the rear wing from this file and put it onto the main body. I believe we had one main testing body that we used for our flow design, and also utilized ANSYS ANSYS.
Fluent, CFX.
I can't remember the name of it, to be honest.
Yeah, there are just two actually. I think ANSYS Fluent and ANSYS CFX.
Yes.
Yeah, Fluent, I believe it was.
Yeah. The more complex one.
Yeah, that it took a while to get working. It was closing into the final stages of development where we were delving into ANSYS, because it was, whilst worthwhile, definitely getting working. The data it provides is incredible compared to flow design, but yeah, it definitely took its time.
Yeah, regarding parametric design, I think first thing is to really stop to think in one direction. So when you design your CAD model, stop to think in one direction. That means you always should be able to come back to a previous point. So you should think in a two-way approach. So once you design your complete car, you need to be able to step up in an area of it to be able to change it, and still everything works afterwards. Like changing the width of the car and for example the basic parameters, you should be able. Then everything else is updating itself. Then you should think about what do you actually want to control. I mean, with the wing at the F1 and schools car, for example, let's take the rear wing. You actually don't want to change the thickness that often, right? So I guess you want to keep the thickness at the minimum, as the interaction with the air should be as small as possible. That means you might be not interested in changing the thickness, so you leave out that parameter, for example, as a constant. But you would like to play with the width and with the length of it, and or with the position. So what you then gonna do is you could, for example, define a 2D sketch somewhere in space around the rear of the car, in that area where it's allowed to have that piece. And then you would like to move that sketch in on the symmetry plane. But doing that, for example, when you move then the swings to a lower area, you actually need to move it then wider, right? Because you need to fulfill a minimum width. So what you could do there is you could constrain your design in a way that the minimum width of the wing needs to be always given. So that means you could intersect the outer shell and then think about how you create the offset in a way that it's always that shape. With this, you could analyze pretty quickly or create pretty quickly CAD models with different positions of the rear wing, where you have different angles, different lengths, or maybe try with its shape a bit to be able to influence the characteristics of the rear end of the car. And that's so you try to build up a kind of abstract wireframe or abstract approach first with what you are able to control, and once you have that, you basically make the surface or the solids then happen. I think this example with the rear wing on the F1 and schools car, you could pretty easily do as well with a solid shape and still be parametric.
Yeah, the other thing is to keep down the single steps to have your final model, because when you change a parameter just in one of the first steps you did, you have solver times from or up to 2 minutes or something like that. Sometimes it's quite annoying because you want to make a little change and then see how the car turns out, and it solves 2 minutes. And if you then are not happy with the result, you have to go back and it takes another 2 minutes, and that could be annoying, but that's the challenge.
But then, Ben, you mentioned something where you created basically a modular approach or that you have a huge matrix of geometries in the end from the rapid prototyping point of view. But why are you not doing that, for example, with the CAD files, where you, for example, divide your car into front and rear, or mid, front, rear, or whatever, and then you just change. You have then potentially 3 designers, and then every designer could iterate around his area, and then also the update process might be faster.
Yeah, I think that's basically a good idea, but F1 schools, the rules are quite complex, but they leave you a lot of space to I think in the real F1 everything is really defined, so you cannot try a lot of things, but in F1 schools I think there are different approaches, different car shapes. So if we think of doing another shape, you can't really divide the car in a rear section and a front section, because they basically interact in the same way. But for example, I could imagine doing this for the wings, the rear ports, side ports, and wheels, for example. But the basic shape of the car must be in one file, I think.
Yeah, I think that could be a decent option for the start. Yeah, I actually spoke last week as well with Formula student guys, and they're also starting to dividing their car much more into sub pieces, and then as you described, but the number of pieces is just a bit more, as they have as well the engine and then cooling and then so on. Yeah.
All right, interesting.
We talked about collaborating on the CAD module. So one thing that is important when you have multiple CAD engineers working on a part or project is consistency. So how would you achieve this consistency and avoid conflicts? Starting with Ben maybe, and then to Bilal, how is that done in the real F1 world?
When it came to collaboration within Ascension, we actually had it pretty easy. We had only 2 engineers within our team at the World Finals, Brock and Fefe, and between those 2, they kind of collaborate amongst each other with initial ideas and concepts. However, we had Fefe create the main model of the car in terms of 3D, and then Brock would manufacture the car afterwards. And so whilst initial collaboration was there, coming up with concepts and definitely in the refinement process, the main consistency was kept pretty close, as only one person was actually altering the model itself.
I think the most crucial part is as well the point of communication between the engineers. I think when you can underline that a couple of times, without that you can throw as many engineers into a design problem, and you will come up with something pretty weird. You need to give them the option to exchange each other on regular basis, first of all. Then you define the different areas which each designer should take ownership on, or their responsibility. And once that is done, you let them do their thing basically, and exchange each other. Often enough, maybe not too often, but often enough to show the progress, and as well in which direction it should be developed on, and which problems are more prominent and which are more easier to solve.
So you would divide the part into different sections?
You mean the complete car in different areas? Yeah. So for sure. I mean, you could even go further down. I mean, you have the rear wing, front wing, and all these, each components are then divided into different as they are already different parts of the rules, so you divide them as well in a different part of designers. But the thing, I think the big difference to F1 in schools is that not only 1 or 2 designers are doing basically the complete thing with simulation and designing. You have here then in F1 more the approach that you have for each process step as well, a dedicated person. So a designer would do the shape of the components, and then an aerodynamicist would simulate them, and then someone needs to calculate this regarding stiffness and compliance so that thing is not breaking on the track. And then you have the guys who needs to make design the car components to make them producible.
But how do you assure that the person that is, for example, developing a part on the front wing has the same concept in mind like the person optimizing the rear wing?
That's why you use you need to communicate often. So it's you need to come together, define a roadmap in advance, or basically direction you want to develop on, and that is then coordinated usually by the team leaders or by the head of department or chief aero or any I would say from the leaders. And
Right.
So imagine in F1 in schools, if you would do the F1 approach there, you would have one, let's call it head of design, okay, and then you would have like 3 engineers, where one engineer is doing that part on the car, that other one this part, and then that other one, the final guy who's doing the wheels. And then the guy, the head of design, basically is responsible for that all of these 3 engineers are communicating on the right topics about the car, and that development direction is set up properly.
Right. So I see the problem. And as Janis is is a new team member, we had also the same problem.
Yeah.
Because it was really interesting to see their different approaches. And as you said, communication is the first part, but every design engineer has his own structure or his own way to build those volumes, those shapes. So Janis and I, we had to communicate quite a lot and teach us some things. Maybe you can elaborate on that.
Do you mean that with this the design methodology? So how you design, basically?
Yes, basically yes.
Also design standards.
Yeah. So these are methodologies. Then like the standards. Yeah.
I'd say yes.
Okay. So Janis, you wanted to?
Yeah, I want to say that we before we start to design a car, we set design standards. For example, the length of the car. And after that, one of us designs the chassis, the main part of the car, and then we talk about that, and then we everybody designs rings and other parts of the car, and then we have a few options, and then we look up in the CFD which option is the best.
That's really the advantage of parametric modeling. So it's most of the time one of us who models the basic chassis, but then we communicate and say, what do you think about this idea or about that? And the advantage of parametric modeling is that you can change those sketches and surfaces. So it's a never stopping process. You have those basic design, but then it's important to have those options to change it and make it in that way you really want it as a team.
Yeah, so maybe extending on the metaphor that we had in the beginning. So every engineer has his own handwriting, and in a team it's important to be able to read the handwriting of the others. And maybe that's like the most important thing that you should take away from this section, is to communicate with your other design engineer, if there is one, and that you have the same plan in mind. But moving on, as pointed out in previous episodes, it's essential to build a rule-compliant car. Therefore, you should consider all the rule constraints in your designing process. So how did we do that in the F1 and Schools competition? Maybe, Ben, you start.
Yeah, so we took quite an interesting approach when it came to designing a car with a couple of different KPIs, key performance indicators. And compliance actually took out about 50% of our KPIs in terms of our mathematical model to set that up. So when it came to ensuring our car was legal, we undertook a lot of rigorous testing when it came to our own design constraints and what sort of additives we need to ensure were on the car to create a perfectly legal car. And measuring was constantly taken under every step of the manufacturing process.
So you had then as well like a tracker to see where you currently are and always been able to monitor your development and the progress.
Yeah.
With these KPIs. Okay.
Yeah. In our folio, we had a little almost chart where it had the three individual KPIs stacking up to each other. And that helped us follow the process of the development between each car. It shows us the trends between each one to create the best car possible.
Right. So, when it comes to F1 schools or our team, we adopted the strategy of the real F1. So we have those volumes, those constraints where we are constructing in. And the other thing is to really have the regulations in mind. That's one of the most important things, I'd say. So for all new teams, I think it's the best way to keep on having a look at the regulations, train those rules, and have them always in mind. So you don't have to look them up every time. But I think the most important thing is measuring the rules all the time. Whenever you do a change, check if the change is rule compliant.
And what is the approach at real F1 teams when consequences for slight rule of infringements are as severe as we saw with the disqualification of Lewis Hamilton due to a slight rule break at the rear wing?
Yeah, I think here we need to distinguish between design by so when you design something in CAD, then it might look completely different than in the real world. So we have as well the point of deflection or something breaks or anything is not fixed as it should be due to the problem of something was a boundary maybe was missed in the simulation of the stress, and so there are plenty of things we need to respect. So first, obviously, the shape itself, but then when you simulate it that it's the right boundary conditions as described, for example, when a car, imagine you develop a wing or any shape on the car without the analysis of when the car drives over curbs. That, for example, driving over curbs will create a certain frequency, and that will then potentially in worst case will break any part on the car. And then as well the FIA doing a couple of checks as well on the racetrack as you just highlighted with Lewis. Then you need to prepare basically that already at the start when you have the idea. This means write down the rules you have for the area you work on, create some kind of checklist, or reduce then this kind of couple of lines of text into certain easier understandable checks maybe. And then once you're happy with your design and want to pass this over for manufacturing, for example, then you go quickly through these checks and then to see where you need to improve. So as Florian said, that you should do that always with that in mind when you design anything. So be able to know all the time the details of the rules, and usually you discover more and more details the more you design and the more you check.
I think there are also like possibilities to check your rule compliance within the CAD. Maybe for the rear wing, you want to explain how we did that, Flo? I'm talking about like the rule with the flow, for example, that you have like 3 millimeters flow.
Ah, right, yeah. So So at some point, it's interesting to have some helpers, I will call them. So, for example, for the World Finals, you have those 5 millimeters from each surface point from the rear wing, which does not or is not allowed to interrupt the airflow. So we have those helpers in mind. So we just created an offset surface from the wing, which is in the CAD model, so we can easily see if we have those 5 millimeters not broken.
One thing that interests me personally as we are talking about rules is searching for loopholes in rules. Is there like a dedicated person in a F1 team that searches for these loopholes, or how do you approach working with your with the regulations that you got?
Yeah, that, to be honest, depends on the team. So there are really various different approaches for that. But I think the most crucial thing that I can say is that first thing, you really need to know the rules, and you really need to have a lot of experience, and combining both of these things could come up then with something like a loophole. But obviously the FIA is fighting to reduce this, and as well, once you found anything, people will as well copy that. So once you have an idea and you think you have something, be conscious that teams will copy that, even eventually for the race afterwards or the 2 races afterwards. So yeah, so it's not like you have found the holy grail of whatever loophole, and then you think you are automatically the winner. I mean, it's the competitiveness of the competition that will people will copy that.
Any experiences on that in your F1 Schools team?
To be fair, you guys for sure always look at the winner car from last year, and then you think about how to make that better, right? So this is usually the approach.
Absolutely. I remember, like, you'll go to a competition, and the year after, I remember when Infinitude broke the world record. There were 6 or 7 cars that looked the exact same rock up to the starting grid, and that's just going to happen within anything for that matter. When it comes to engineering, they're going to want the best design. I remember we had one concept that we ourselves developed by making an asymmetric car, removing half of our rear wing because there's technically no regulation, although we didn't run it due to the total stress that was then placed on the rear wing when it was stopped. But within F1 schools, they've kind of patched the whole loopholes. That there's no longer going to be any major loopholes, I feel, within F1 schools due to what they deem spirit of the competition, and that comes up to judges' discretion by the end of the day. So if you do come up with a loophole, I do recommend getting it checked. Shoot F1 schools an email, probably. That'd be my best bet. Otherwise, you may find that your car will be illegal and it's not going to be worth it.
But isn't it when you then ask for it, then it's automatically kind of, anyways, gonna say it's illegal, and then can you not talk about this at the competition then?
If you ask about it, I feel like you'd be more invited to talk about it in your development. However, I know that when it comes to the safety of F1 schools cars, they tend to take that quite seriously, and anything that may be deemed too unsafe, such as the LERS, Launch Energy Recovering System, that was deemed illegal back in 2017, the year after Infinitude broke the world record. That was initially designed as a loophole, and then was deemed illegal a couple of years later. But they've really cracked on it over the past few years.
But then maybe if your team finds a loophole, because all the questions that you ask F1 schools will be like responded to publicly, because they want to make it fair to every team. So maybe if you find a loophole, you should think about if it is worth it, and if you're properly able to argue for it. But then asking for it would make it like useless, because other teams would see the response to your question.
There are loopholes within the competition that I know about that I've seen other teams develop that most teams don't know about. It's because F1 schools tends to keep their communication quite close with the individual team. And this team in question I'm thinking about in particular had discovered a certain loophole that was sped up the car quite significantly, and F1 schools deemed it not to be spirit of the competition. So,
all right.
Yeah, I think in F1 you have a bit like a similar thing that if you ask the FIA for certain areas which are not that clear, then the FIA needs to write a clarification afterwards, and that's gonna be sent as well to everyone. So, and then this is then as well studied from them, and they wanna know then what you're working on. Especially right now where all the rules are completely new, every hint or any kind of idea how to think about this is could be a kind of reveal of where you are in the development process.
Right, yes.
All right. So once you're done with designing the final parts, you may want to create an assembly. Any thoughts on how to do that and why it is practical to do an assembly of all your parts in the CAD process?
Yeah, I think it's common to do that, yes. It's no question, but I think you have all those parts, and as we had the topic before, you have to check all those rules, and the best way to check the rules and measure those parameters is an assembly. So you basically connect all the parts together correctly. That's important. So all parts are defined and have those relations in between. So when you change your cars, the assembly changes too. I think it's more for checking the rules.
And I think it's important to check if the parts are right connected when you produce all of the parts. And you can check the weight of your car if you know the material data.
Or the weight distribution as well, right?
Yeah, that's a good point. Right. So, and that's also the step in between designing the car and then exporting it for manufacturing processes, because or for simulations, for example, because you don't want to check the rearing as a single piece, because you want the whole car, the whole front, for example, to check in the wind tunnel. So you have, in the end, you have to do somehow an assembly to check your car for aerodynamics or rules or connections, whatever.
Or tolerances as well.
Yes, right.
All right. So moving on to the next big part, which is technical drawing. For the competition, you have to submit a technical drawing with which you should be able to assemble the car, but also manufacture the different parts. So my question would be like, what was the approach in the competition for doing such a technical drawing, and maybe getting the insight from Bilal as well, how he would do such a technical drawing?
Technical drawings within Fusion 360 are quite easy. There's just a drawing workspace that you could enter, and when highlighting a part, it will create a drawing of a specific part. You can change different line widths, different line types. You can also include different regulations. I know we had our virtual cargo outlined in technical drawing. That was done by just creating a physical block inside the car that represented where the virtual cargo was to the exact specifications, and just putting that as hidden detail. So within Fusion 360, it was relatively easy. You also want to be extensive with your technical drawings. Don't want to leave out any detail. I remember it being explained to me once as a judge should realistically be able to sit down with a computer in front of them and rebuild your car to the exact specifications. So if you can't do that yourself, then how is a judgment to?
Okay.
Yeah, and I think the best approach for new teams, especially, would be to have a look at the rules, because at the end of the rules, there's an explanation of the more or less basic technical drawing. It's, I think, a good reference to begin a new technical drawing if you have no experience. So I think that would be the best approach for new teams.
Yes, and I think every CAD software have part where you can produce a technical drawing. Solid Edge also.
Yeah, I think it's quite important to know the purpose of the technical drawing. So do you want to make it for assembly? Do you want to make it for the manufacturer? Or do you want to make it for the legality? Or do you want to make it for anything else? So let's take, for example, the virtual volume as in the F1 and schools cars. You might not need that virtual volume for someone who's manufacturing that thing. Is might be only important as well, not important for the guy who's assembling the car, is only for the regulation checks, for the scrutineers. And so once you know for who you make it, this drawing, just make it as simple as possible, because adding more dimensions, adding more tolerances, adding more anything to it will just make it more complex to understand, and it takes more time, and as well you potentially will oversee anything. So imagine you give someone who's manufacturing the axis of your F1 and schools car, you will not need the BOM of it, so the bill of materials, so which components now needs to be assembled together. So you just want to know the tolerances, the width, the length, and imagine you need to produce that component yourself, just put also that information on it. And for someone who needs to assemble something, I think it's as well important that you have your bill of material on it to see which components you need, or what process you need to do with these components, like do you screw it, or do you maybe need to glue some stuff, or being able to see which part goes.
Yeah, so the thing is, in the regulations, it said that the technical drawing should be there for assembling the car, producing the car, so the parts of the car, and it is recommended to label the relevant technical regulations. So would you suggest to divide the technical drawing in different parts, so to have multiple engineering drawings that you submit, one for each purpose?
If that's allowed, yes. I mean, then you can write as well on the drawing, for example, that this one is for this and that for that, as the guys who are anyway curious and wants to see more, he can take just all the three together. And but I think making it more dedicated reduces the amount of information you have on one paper. Do you like to read, for example, newspaper where a bit only text is on it and super small written and then 10,000 lines? Or is it also interesting to have a picture next to it, which helps you to illustrate what you're talking about, and a bit, show only the core important information facts.
Great. So once you've finished with your CAD, you may want to export it to another program or hand it over to a manufacturer. And for that, it is important to understand that there are different data formats out there. And we could talk about them in the next section of this podcast. Maybe Flo, you want to start?
Yeah, so basically, as we talked about earlier, you have those native data formats of the different software. And you have those neutral data formats, as you could call them. So in Solid Edge, you have those .par and .asms. And if you want to export them or use those CAD files in other programs, you have to use different native, or you have to actually use neutral data formats. There are different ones. I could imagine .igis, for example, or .stl, which is pretty common to use for 3D printing. The data format we use most for exporting is the .stp or .step file format, because it's a industrial standard and almost every software can read it, and you have lots of information stored in that file.
Yeah, so maybe to give you like a quick overview, like the IGS format that Flo talked about is like a format where your model is exported into a wireframe, and it may be good to use that format if you want to do like iterative analysis, like a CFD analysis or a finite element analysis. Then you might want to use IGS. And as Flo pointed out, like STL is more the format that you might use in 3D printing. And the format that we use most commonly if we want to communicate with our partners, with our manufacturing partners, is the STP format, because it's easily accessible for the manufacturer. But maybe, Bilal, you want to give the technical background of these formats?
Yeah, sure. So, you need to divide between, as you said, the native one, and then you have these formats which are easy to share, but these are more mathematical described surfaces, as the STL, for example, as stereolithographical is called. You have like a points which describes then over triangulars the shape of your geometry, which are more pretty. It's not representing the right mathematical shape. For example, for a circle, you basically discretize a circle into points, and then makes it a bit more edgy. If you would think about, so the more points, the higher resolution, and the more detailed info you will get. This is more required for printing, as described, or as well for CFD or virtual wind tunnel, as you call it. Then you have these formats like STEP, IGES, and that's the two most common, I think, which are used then more to exchange that geometrical information with suppliers, that they can use them for their manufacturing bits like CAM processes for their CNC machines. So they can calculate then their tool paths with that properly. So with the STL, that might be a bit weird. And then the native formats you exchange within your team usually.
All right. So thanks for listening to this special episode of Off the Track. Remember to follow OTT on social media and to follow at Team Sonic Boom as well. Goodbye.
Thank you.
Bye-bye.
Bye-bye.
Thank you for listening to Off the Track. If you enjoyed this episode, rate us 5 stars on Apple Podcasts.
It really does help.
And share the podcast with someone else who may find it useful. Stay up to date with us by following us on Instagram @Off the Track Podcast, and visit offthetrack.net for the latest news.